Okay, everyone, we're going to get into statistics and a bunch of other stuff today. It's this big grab bag of math. Um, I wanted to say that I when I looked over the survey, the chat responses you gave me for our first lecture, I was pleasantly surprised slash a whole lot intimidated, and maybe my inferiority complex is going to start popping out here. Many of you have backgrounds in either using Tableau, using Jupyter Notebooks, Python programming, databases, machine learning, all sorts of all these topics that directly relate to this course. And although I'm very, very clear about, I hope I'm clear about saying that this course is not about machine learning, but we might be using it, or that it's not about using Tableau, but we will be learning it. I still have to cover topics that you guys may know more about than I do. And I'm okay with that, well, within within reason. I'm a little bit intimidated. So just letting you know, if there's something that I talk about that you go, well, actually, technically that's wrong. Let me know. We can make. I want to make sure that we're clear and that I'm correct. I'm willing to forego my pride if I said something wrong. Most of the time, that for all these topics, we're covering just the surface. We're just scratching the surface of these topics. So I don't think I'm wrong. But if I am, please let me know, because some of you know more about this than I will ever know, because it's your area. When we get to visualizations and human factors and all sorts of things like that, it's my area. I'll know that stuff. But when I talk about machine learning, we're going to be hitting things that I will look up if I have to use it. Like if I have to do a multidimensional scaling algorithm, I will look it up when I need it, not beforehand. So I'm not the world expert in MDS, for example. This is one of those examples. We're going to be looking at stats, machine learning. There's a lot of statisticians out there. I'm not a statistician. I learn it enough for what I need. When I do my research, I look up the stats I need for that. I'm going to be giving the overview of how to envision or think about your stats. But when I get to doing my statistical tests, I'm breaking out Google. I'm breaking out a textbook. I'm looking at what I should be doing based on the data that I have. So we're going to give you the framework, but not necessarily the deep nitty-gritty details. Just so essentially enough information to be dangerous. I'm also going to be going over a lot of other things along the way. So it is a bit of a grab bag of different topics. Actually, probably shouldn't be. It's just lecture 5, and it's just going to cover however many lectures we need it to cover. And I'll point out where you should have watched all these videos by the end. It'll approximately match to, or will match, the course outline, but I just put them all in sequence in one series of PowerPoint one slide deck. Okay, so presumably when we're watching this today, what's due is nothing, and this week homework 4 will be due on a Friday. This is the time approximately when you should be watching this video, but you can watch it in advance if you want. Task analysis is fast approaching, and so that would be for lecture 3's work, when we're looking at why are people looking at your data. Not how you're analyzing your data afterwards, but why the heck would anyone want to use this data set? And that's a big part of this course project. Something I'm very passionate about, at least. We're going to look at all sorts of kinds of data, but first I want to give a general framework. So summarizing quantitative data, this is quantitative data, not qualitative data, which is different. I could give a whole lectures on qualitative data. That's actually where more of my training is. It's a bit of an anomalous or weird training for computer scientists, but so to give you some background, I may not know Tableau as well as you guys do, but my supervisor is now at Tableau Research, so she's actually pretty big in Tableau, but she is a big qualitative research person for visualizations. So why do people use a visualization? How are they using it in real world contexts? That's a very different beast than quantitative data, looking at numbers. You're not doing qualitative data for most data analytics simply because you can't like mass store interviews, right? We are looking at numbers and how they can be analyzed, not necessarily trying to find patterns but those qualitative approaches are still useful for when we're talking about how we design a system. So these interviews that you're going to be doing for task 2, that is more of a qualitative approach. You're not looking for, he said it 50% of the time. He said this word 20 times. You're looking for the thematic aspects of the data. You're looking for the overall structure. You're looking at the high level picture of the domain, not necessarily counting numbers or frequency of words or statistical chances that I said that word instead of this word. They are different beasts, and we're going to focus here on quantitative, but there's a whole other field, a whole other world in terms of research for qualitative. Okay, so we've already talked briefly about these 4 different kinds of data, and people will break this problem down into other things. So we have nominal, ordinal data. Both are considered categorical data. So nominal would be things like countries. Ordinal would be things like a Likert scale or like coffee cup sizes, right? They go from small, medium to large, but the interval between the two, I don't know. What is a small compared to a large? Well, I don't know, but I know it's larger than the large is larger than the small. Or if it's not, well, there's problems. We have the interval data. The space between them is known, so the difference between a 4 and a 6 is known. There's a difference in the space of 2 units, but at the same time we don't have 4.29732. Ratio or continuous data is things like anything that be represented by a fraction. Heck, I'll even let you put in the irrational numbers. So if you want to look at this is a set of rational numbers. Traditionally, at least, we have to have some upper level of precision. So this can be represented as some kind of fraction. It's rational numbers. We have the interval numbers. Fine. This would be, there's actually ordinal data structures in C++, Java, and in most other languages where it is just, they're categorical data, but they're ordered. And then we have nominal data, which is things like color. We also have unstructured data, but we're not going to be going into in order to do a statistical test, you need to break it into one of these formats. So let's have a quick look at some of this stuff. So do I have categorical, ordinal, interval, or ratio data? Or, I think all of these will work actually. So what do I have here? Age. Depends on the age of the kid, actually, I guess. You could say it's ratio because people, if you're 4, you say, I'm 4.5 years old. But when you get to my age, you're lucky to say you can get an age from me. I think I'm 45. Gender. Also, you could consider it a bit tricky, but I'm actually going to make sure that we are more inclusive, not just male, female, but male, female, non-binary, and prefers not to say, or you can throw extra categories in there just to make sure that you are including everybody. But I'm going to avoid being sexist and say it's not ordinal, right? It's categorical, or we probably should say nominal, right? I have different categories. I could bucket people, but you're not going to say, men are better than women or anything along those lines. That would be terrible. Job category, you would say it's categorical, but engineers keep saying that they're better than everyone else. But I would say it's categorical. Or how efficient or something. You can actually have some kind of ratio data structure. It's continuous data. School year. Depends. Canadian University makes it a lot easier, right? First, second, third year, and fourth year. That's interval. Although it gets a little wonky with, extra years if you have a co-op. The U.S. system has this freshman, first, junior, senior thing that I still can't get, even after all this time. But yes, I would say normally you could say ordinal, but I would say interval, right? You can map it clearly to a number. You know the difference between a freshman and a senior. It is 2 years. But you could call it ordinal if you're saying that people can take extra time and they're, that's my second year as a freshman. Temperature is ratio. You have effectively infinite precision. You can say it's 39.29732 degrees Celsius. How about quotes? Now, I would actually call that categorical or nominal, if you want to say it more precisely, right? It's not like one quote is better than another quote. You cannot order them necessarily, unless maybe you can. There are some times that you could find a way to force it into some kind of ordinal data, but for the most part, we're going to say categorical. Productivity, words per document, and owns a pet, yes or no. Owns a pet, yes or no. That's an interesting one. Oh, rain also is nominal or categorical data, right? If there's no ordering necessarily. Owns a pet is Boolean. So what is that? I own a pet or I don't own a pet? I'd say that's interval. I know the difference between the two of them. I could order them. You could say ordinal data, but you could just map it to a number and you're good to go. So one way of looking at it, I'm not going to be hardcore on most of these things. People make honest mistakes, especially when things get a little bit wonky. Unstructured data really throws people off, right? It's, you give me a bunch of text. Is that ordinal? Is it categorical? Well, it depends. Can I map it to something? All of these categories, if you can map it to a rational number, can you map it to an integer? Can you map it rational number? And it makes sense to map it to a rational number, I should say. Owns pet or yes or no? No, that's categorical. What am I talking about here? Why? Because is it better to own a pet or not? Map it categorical. There is no number you map it to. If you have ordinal, you can sort of map it to a number, but not really. You get, it's biggest. If you think of it that way, it's using the greater than sign versus giving an actual number versus giving an actual ratio versus it is what it is. Nominal data. All right. What we want, however, is we need some way of analyzing our data. And this was bigger for my Viz class and for my HCI class, but it comes into play here. So we're just going to quickly go over this. And again, if you know your stats, don't worry about it. You can skip ahead a lot of these slides. So we're going to be looking at, if we're looking at a bunch of statistics, or we get a bunch of statistics, or we want to see how much people liked our system, we need some kind of statistical measure for it. Descriptive statistics say this is what the data actually looks like, and here is a way of describing the data without showing you all of the numbers. So we can focus on correlations, dimensionality, scaling, and data mining later, but it's, if we're testing our system, this is what we want to report. What is the mean, or what is the median of our data? What is the distribution? How does it spread out? If I'm looking at my classes, I'm looking at what is the mean and the standard deviation of my exam scores. It accurately describes what's happened. It doesn't tell me how everyone did. It gives me a high-level view, a fairly simple way of summarizing the data. It's summative statistics. It describes what the data set looks like in a high-level way. It hides a lot of the nuance. And as a result, because it's hiding that nuance, you've got to make sure that you're using the right test or you're using the right analysis. So if you do not know what a histogram looks like, this is a histogram. You know, how many people are in each of these buckets, right? There's this number of people that gave me that response category 4. There are this many people that give me response category 2. A normal distribution is a bell curve. When they say curving the exam, this is what we're inferring. That if our exam scores are normally distributed, we can shift everyone over and the stats will work out for us if we are intelligent about how we do our transformations. If we do not have a normal distribution, if it does not look like this bell curve, then you have to do something different. And normal distributions are normally everywhere, or we overly assume that they're everywhere, which is one of the little problems with a normal distribution. It's not a problem, but people overgeneralize. So people will do an analysis of variance called an ANOVA for everything in my field, even if it doesn't make sense, even if the data doesn't support it. They will do an analysis of variance. So here would be two cases where I'm not supposed to be allowed to use, I'm not supposed to be using, I'm not assuming that there's a normal distribution because it's a skewed normal distribution. It is a positive skew, as in it goes long on the top end, or a negative skew, so it goes long on the tail end. I normally have my exams look like a negative skew normal distribution. There is always someone that can fail it. There's a bunch of people in the, the B, A range, that sort of thing. There's a bunch of people in the A range. No matter how hard I make an exam, there's always someone that gets 100%. And there's always a whole lot of people down in the 40s, 30s, 20s, all the way down. This is what the average or the typical university score exam looks like, right? I really screwed up if my if my distribution looks like this for an exam. There's one person that got 100% and everyone got 30. That's terrible. You can compensate for positive or negative skew. You would look that up when you find out you have a negative or positive skew. You'd figure out how to do the stats for that. To shift all the numbers to form a normal distribution and then do your stats. Mathematically, it'll work to compensate for the skew. Bimodal distribution, which is what I always think of for computer science classes, I've been told that they don't actually bimodally distribute, but I'm still not 100% convinced. I always think of, when I think of my classes, for programming classes, for example, or any math classes, you get a bunch of people that will get an A no matter what you do, no matter how hard you make the course. There's a bunch of people that get an A, they just get it, and they're naturally, this talented set of people that just naturally get the topic area. And these are the people that are really, really trying really hard, but they're mere mortals and they have to work at what they're doing, versus these people just get it. Bimodal distribution is fairly common in a lot of STEM programs, but I've been told, and I can't prove that it's bimodally distributed, it's not as frequent as one would like to think. But if I have a bimodal distribution, I can't run normal what are called parametric tests. I cannot get the mean. The mean means nothing. The mean of this thing is probably 75. And so everyone thinks, hey, the most people's mark in this course is a 75. Look at it, it's right here. Most people do not have a 75. It's telling you the wrong piece of information. So we actually have 3 different measures of center. We have a mean. So I'll see if you guys can recall them before I actually go over the definition. So what does a mean? Okay, most of you remember that it is you sum up all the values divided by the number of values you have. That is what we normally call the average, but all 3 of those things could be called the average. Technically, the average is actually a nebulous term. But when we talk about the average, we normally mean the mean. The median is what? It is the data point in the center of a distribution. The median is less skewed than the mean when it comes to calculating an average. So if I have, let's say, there you go, with this negative skew, the mean is, about here, let's say. There's a bunch of people that have got like a 2% on the exam, and they've thrown everyone off. This is the throwing off the curve thing that people talk about, right? There's one person where the mean is now here because someone's getting a really low mark here. The more important one would be here, right? If the class gets a 30% and one person gets 100%, they throw off the curve because now the mean is like here. The median is right there, or approximately right there in the middle. It is the center of all the points that you get. You get 4,000 people. The person, there's 4,001 data points, let's say. The median value, there are 2,000 people below you, there are 2,000 people above you. You are smack dab in the center. If you have an even number of things, you take the average of the 2 median scores. So the median doesn't have to necessarily be an actual number that people get, but let's pretend it does. Right? For the most part, it's going to be an actual number people get. The mean doesn't have to actually exist. Like if you take the mean, nobody may have gotten that number. They may have gotten close, but they may not have actually gotten that number. The median, oftentimes there's an actual person with that actual value. And then there's the mode, which is the most frequent of the various things that you've gotten. This is terrible for anything that's like continuous data or interval data. It's the only game in town for categorical data. What country, if you're talking about, country of origins for you guys. Okay, the mode would be Canada. That does not necessarily mean, like, you can't order countries. They're not better than one than the other. What's the mean country for of origin for you guys? It makes no sense. What's the median? That makes no sense. The mode is the only thing so it's the most frequent answer. The most frequent answer is, I'm presuming, based on what we talked about, Canada. Some people may be international students, but most of the people in the class, or the most frequent single country in the class, is Canada. even if even if the class was mostly international students, you would still have the mode of being the most common thing might still be Canada, because they would have to all be from the same country otherwise. So what about Ottawa rent prices? What do you see when you talk about rent prices? When people say what's the average rent price in Ottawa, what do they normally use? The mean, the mode, median, or the mode? Well, they use the median. And why? They use the median because, if you hadn't noticed, Ottawa has a pretty big spread when it comes to prices. Boston was brutal. So the original slide for this was for Boston, and Boston is like, you can get condos and houses and stuff like that in the tens of millions of dollar range, and then you can get places that are $1,000 a month or less. The median means that there's no upper limit to the amount of the maximum price, and so it really skews things. The median price for a house in Boston, let's say, is I think it's probably $600,000. The mean price of a house in Boston is probably $1 million and a bit, because it's so skewed. Well, maybe not $1 million, but 900,000. It really skews it up because of really ultra wealthy that live in Boston, and so the median is a better fit. It is a positively skewed distribution. So we've already talked about most of these things, in case you want to look at the values again. The median, if the data is skewed, if I have a problem that there's extreme outliers, the median is relatively insensitive to outliers. The mean is extremely sensitive to outliers. And it's so the median, although may not seem like a better score, in some case it is the only game in town. So if I have nominal data, then I want to use the mode. Otherwise, if I have interval or ratio, I want to try, and I have a normal distribution with no outliers, I use the mean. Otherwise, I use the median. Okay. And things really aren't that simple. So we're going to be looking at distributions next. The students, by the way, the term student t-test is actually based off of a pseudonym, a pen name for the statistician that was doing it, not necessarily because he was a student. I find that fascinating. So we'll get to that in a second. So we want to be able to we are making a lot of assumptions about our data and what kind of analysis we're doing. We're looking at correlations. Is there a correlation between these two data sets? We're looking for outliers, whether we can throw away certain people's numbers or data. We're looking at an analysis of variance, for example, maybe, where you're looking at how distributed or what the distribution of scores are for one group, the distribution of scores for another group, and seeing if there's something there, if there's something unique about it. So, for example, the vaccine, when they're testing these phase 3 vaccines, they are giving a placebo to a large swath of the population. They're giving the vaccine to a large swath of the population. They're hoping for a truly random representative sample of the population. That's actually very challenging to do for vaccine research, because some communities are not as trustworthy, or not trustworthy, do not trust the medical community. That's the other way around. They do not trust the medical community as much as other communities. For example, the black population in the United States traditionally has not been very trusting of the medical community, and for damn good reason. If we get to the ethics of research, I'm not sure we do for this class, there's the Tuskegee, if I'm pronouncing the town right, trials was a travesty. They were giving syphilis to people to see what effects would be, and not telling the people that they were infecting with syphilis. And they were only infecting black men. They were not affecting the white population, although the research was going to help people. It was going to hopefully help the population in general. But even when they got antibiotics, they were not allowed, the people in the Tuskegee syphilis experiment who did not know they were given syphilis were not allowed to take the antibiotics. They were working around out of their way to prevent them from taking it. The people that were benefiting from the study were not the people that were being, the study was being done on. So getting a representative sample can be challenging, because they're rightfully so in many cases, There are some groups that do not trust the medical community or do not trust the efficiency of vaccines or whatever the case is. On top of that, when we're talking, so this is about random sampling, but even when you get a random sampling, what they're doing with a vaccine is they're looking at the people that get the placebo, what is the rate in which they get COVID, and they actually have to get sick. They actually have to test positive for COVID-19. For the people that get the vaccine, what is the rate in which they get COVID-19? And then you need to see the variance in those populations versus those populations, these two different populations, and seeing how much variance, how frequently they get sick, and is it just purely coincidental that they get sick? This is what an analysis of variance gives you, but it only works if you know that the two populations have a normal distribution in terms of their responses. That's the kicker. If you do not have a normal distribution, you don't get squat. You got to do a different kind of test, and that's why you have to test for whether the data is normally distributed or not. So we have three different measures of spread. These are how the data ranges. We have the minimum and the maximum. That's the range, right? The maximum minus the minimum, that's the range. The interquartile range is you take all the range of your data and you say a quarter of the people are in this range, a quarter of the people in this range, a quarter of the people in this range, a quarter of the people in this range. The median is, let's say, right here in the middle. So interquartile range, when you visualize it this way, it's here's the max, here's the min, here's the median, here is half of my data is in this block right here. And this is the box plot, by the way. So third quartile, first quartile, this is half your people. You have another quarter here, you have another quarter here. Although one quartile seems like that seems off, but okay. This is essentially giving you the amount of spread where the most people are around in this area, and then it spreads out here, it spreads out here. It tells you how big the range is, but also how clumped it is. If you have a small little box here, it means everyone's tightly bound around the median and I have extreme outliers. If this box is huge and a little tiny whisker at the end, then it's a very spread out distribution. And then we have a standard deviation, which is a calculation assuming a normal distribution. Well, actually, I think we have do we have a picture of it? No, I don't. The standard deviation is if I have a normal distribution, it is, I bind it by, based on the variance of the data, how varied it is. I have a calculation for the variance, and I'm trying to figure out one standard deviation is, one standard deviation on either end is 68% of the population, two standard deviations on either end, and we can actually draw that out. There we go. Here's our normal distribution. Should be about 68%. Two standard deviations is 95%. And I think 3 is 99.4, something like that. And you may have actually seen this before. The standard deviation and this range and this breakdown is actually the basis of the IQ test. An IQ of 100 is meant to be 100 is right there. You can say that the IQ test is extremely it's biased in a whole bunch of different ways, both in terms of education, where your background is from, where you grew up, based off of it's racially biased as well. There's a whole bunch of different biases that they try and compensate for on a regular basis. They're constantly trying to improve it, but there's always still some problems here. But if you assume, and it's not a right assumption, but if you assume it is actually measuring intelligence, the idea is that the average person, the median, or the mean, is right here at 100, and it should always be at 100. This is 115, this is 130, this is 145. At 15-point intervals in either direction is one standard deviation. So if you have an IQ of 145, congratulations, you're smarter than 99.4% of the population. More than that, but yeah, about 99.4% of the population. That's why when someone says, I have an IQ of 200, you're like, yeah, There's like 10 people that have that on the planet Earth, so good luck to you. No, you don't. A 145 is extremely rare. It's not impossibly rare. You meet them in academia all the time, but they're probably not me for sure, right? But this is a normally distributed system. That's what the IQ test is based around. Is each of these groups of 15 is another standard deviation over to one side. So an IQ of an 85, though, is 68% of the low end. So this is the 85 here. And below this, right, it's 60, right? No, it's 70, isn't it? 15 each time? Yeah, so 70. If you have an IQ below 60, it means the vast majority of the population is more intellectually capable, supposedly, more intellectually capable than you. And therefore, that you have special services for compensating, right? That's why we have these lines where we do. And you can disagree with the IQ test as a general principle, and I fully agree with you disagreeing with it, but that's the premise for why it's designed this way. Not whether it's right, but how it's designed. Okay, we also have this, so here we have a range. It's the lowest from rest of the highest. Most of you are used to it. Interquartile range is a rough estimate, but it's less sensitive to extreme ranges. The maximum minimum, still, the extreme scores still throw things off, but that block smack dab in this middle, where half of the data is, that's still fine. It doesn't get pulled off by an extreme score. An IQ score, like a standard deviation, does get thrown off. One really extreme score, if you didn't remove it, it will throw off your data. The variance is the squared, so you take the average. The idea of a variance is you take the average score, you take the squared difference between a given score and the average. You square it. You sum up all those. It's the average squared deviation. So you square the difference between. I think my wife's going to do a meeting. You take any given score. You square it from the difference between the mean and the score you have. You square it. You average all those. That's the variance. And then you take the square root of the whole thing, and that's your standard deviation. It's very, very common, but it doesn't work unless the mean makes sense. The whole thing is based around the mean, and if the mean is wrong, the standard deviation doesn't work. So, if I have nominal or ordinal data, stop. There's no don't worry about spread or anything like that. It doesn't make sense, right? So what is the range of countries that you guys have reported? Well, I can see the total number of different countries you reported, but there's no spread. It's just a count. If it's interval or ratio and it's normal and there's no outliers, you go standard deviation, otherwise interquartile. So you have to know how your data is distributed before you do these tests. And after you've done these tests, before you do your analysis later, you need to know what the data looks like. This is why we have a data exploration phase when we look at our numbers at the end. That's why we have an exploratory phase when looking at our stats. So I'm going to pause the video right here, and then when we come back, we'll be looking at more wonderful new things about statistics. All right, thanks everyone.